The latest breakthroughs suggest we may have only scratched the surface. Liking this video helps us share these discoveries with more curious minds, and subscribing ensures you'll never miss a chance to explore the universe's secrets alongside us. Let's journey through the stars together. There are alternative theories that attempt to explain the observed anomalies in the orbits of trans-Neptunian objects, TNOs, without the need for a hypothetical ninth planet. Although these theories are less popular, they offer intriguing and potentially explainable scenarios that take into account other factors, such as the Oort cloud, galactic tides, or even the possibility of a primordial black micro-hole. One such alternative is the hypothesis that the anomalous TNO orbits might be the result of the influence of the Oort cloud, a vast region containing billions of cometary bodies located between 50,000 and 100,000 AU from the Sun, roughly a light-year away. The Oort cloud is thought to include two distinct regions, a spherical outer cloud and an inner disc-shaped region. The objects in the Oort cloud are largely composed of water, ammonia, and methane ices. Astronomers believe that these objects formed near the Sun and were scattered far into space by the gravitational effects of the giant planets during the early stages of the solar system's development. The Oort cloud remains poorly studied, and its existence has only been confirmed through indirect evidence. However, scientists speculate that it might exert a gravitational influence on TNOs, causing the clustering of their orbits and other anomalous phenomena. Another theory suggests that galactic tides, that is, forces acting on the solar system from the Milky Way, could influence the orbits of TNOs. Galactic tides arise from the uneven distribution of mass in the galaxy and can cause slow changes in the orbits of objects at the edge of the solar system. In this context, scientists consider the possibility that these galactic tides, rather than a ninth planet, are responsible for the observed clustering of orbits. These tides could explain the anomalies without requiring the existence of an unknown large object in the solar system. An even more exotic hypothesis proposes that instead of a planet, a primordial black micro-hole might exist at the outskirts of the solar system. Primordial black holes are hypothetical objects that could have formed right after the Big Bang, and unlike ordinary black holes, may have a mass significantly smaller than that of stellar black holes. If such a micro-hole has a mass comparable to that of the ninth planet, about 5–10 Earth masses, it could exert a similar gravitational influence on TNOs, creating the same anomalies in their orbits. Scientists at Durham University in the UK suspect that instead of the ninth planet that researchers have been trying to detect recently, a small black hole might actually be roaming the edges of the solar system. This theory was discussed in the journal New Scientist. However, detecting such a black hole would be extremely challenging, as it does not emit light and can only be detected by its gravitational effects. Despite the appeal of these alternative theories, each of them faces certain challenges and requires additional data for confirmation. Each theory adds intrigue to current research, and in the coming years, scientists may find an answer that will revolutionize our understanding of the structure of the solar system. The hypothesis that the proposed ninth planet is actually a primordial black hole opens up a completely new perspective on possible objects lurking in the distant corners of the solar system. Unlike ordinary black holes, which form from the collapse of massive stars, primordial black holes can be very small in size and have masses comparable to those of planets. One of the main arguments supporting this hypothesis is the fact that black holes of this size do not emit any light and can only be detected through their gravitational effects. However, if the ninth planet is indeed a primordial black hole, astronomers face a new challenge: how to detect an object that is virtually invisible to our telescopes. European physicists have developed an approach that uses data on the oscillations of the orbits of global navigation system satellites to search for possible traces of the existence of so-called primordial black holes. These measurements can help to find or significantly narrow down the field of permissible sizes and masses of these objects, the researchers write in a paper published in the electronic library arXiv.org. We have proposed for the first time to use measurements from gravimetric scientific instruments and the orbital parameters of global navigation system satellites to search for anomalies caused by clusters of dark matter and primordial black holes that approach Earth at a sufficiently close distance. The effectiveness of this approach has already been tested using one of the satellites of the Galileo navigation system. The strength of this radiation is too weak for such black holes to be detected by any existing telescopes. A group of European physicists, led by Professor Sebastian Claes from the Free University of Brussels, Belgium, has developed an approach that indirectly uses existing navigation satellites to search for primordial black holes in the near vicinity of Earth, as well as to search for small clusters of dark matter. Guided by these considerations, the scientists calculated how well a single satellite from the Galileo navigation system, or the entire fleet of these probes, would be able to detect primordial black holes. These calculations showed that a single satellite could detect such objects at a relatively short distance from Earth, about 1.5 astronomical units, the average distance between the Sun and our planet. But combining data from a large number of satellites would dramatically expand the search limits for primordial black holes. Nevertheless, the hypothesis of a primordial black hole remains highly speculative and requires further research and observation. So, is the ninth planet a lost planetary body, or is it one of the first black holes in the universe, hiding right under our noses? One of the most significant challenges astronomers face in the search for the ninth planet is its presumed immense distance from the Sun. At such a distance, sunlight becomes so weak that the planet receives thousands of times less light than Earth. This means that its albedo, the ability to reflect sunlight, is extremely low, making it virtually invisible to most telescopes. The vast distance and faint brightness make the ninth planet extremely difficult to observe, even with the most powerful ground-based and space telescopes. For example, telescopes like Subaru, an 8.2-meter optical telescope owned by the National Astronomical Observatory of Japan and located at the Mauna Kea Observatory, and the James Webb Space Telescope, with its large 6.5-meter diameter mirror located at the Lagrange point L2, while highly sensitive, may still struggle to detect an object with such low levels of illumination. Even if the planet does exist, its visible brightness, or apparent magnitude, might be so small that it gets lost among the millions of other stars and objects in deep space. Another difficulty is that, according to models, the ninth planet not only has a large distance from the Sun, but also follows a highly elliptical orbit. Such an orbit could take from several thousand to tens of thousands of years to complete a full revolution around the Sun, and depending on the current position of the planet, its detection could be even more challenging. If the planet is at the aphelion of its orbit, its farthest distance from the Sun, it would be even dimmer and harder to observe. Additionally, the planet's slow movement in its orbit means that reliable detection requires years of observation. If astronomers detect an object that matches the parameters of the ninth planet, they will need to confirm its orbital motion, which can take years. Such long-term observations require significant resources and careful planning, as telescopes capable of such studies are often occupied with many other scientific projects. Modern astronomical observation methods also face several technical limitations. For instance, ground-based telescopes are affected by atmospheric and weather conditions that can distort images. Space telescopes, like the James Webb Space Telescope, although free from these issues, face limitations regarding observation time and spatial orientation. The search for the ninth planet remains one of the most exciting challenges in modern astronomy. Leading observatories around the world continue intensive observations of the distant edges of the solar system, using both ground-based and space telescopes. Each of these tools has unique capabilities that may play a key role in detecting the hypothetical object whose gravitational effects are felt on the orbits of trans-Neptunian objects, TNOs. One of the most promising tools for finding the ninth planet is the Vera C. Rubin Observatory, set to begin operations in January 2025. The official start date for the project is considered August 1st, 2014, with construction on site beginning April 14th, 2015. The telescope will be located at the peak of El Peñón on Cerro Pachón mountain in the Coquimbo region of northern Chile, near the existing Gemini and Southern Astrophysical Research telescopes. The LSST, Legacy Survey of Space and Time Architecture, is unique among large telescopes with an 8-meter mirror and is designed based on the Paul Baker three-element scheme. This design is capable of providing a very wide field of view. Its diameter is 3.5 degrees and its area is 9.6 square degrees. Achieving such a very wide, undistorted field of view requires 3 mirrors instead of the 2 used by most existing large telescopes. The primary mirror has a diameter of 8.4 meters. The secondary mirror is 3.4 meters, and the diameter of the tertiary mirror, located behind a large opening in the primary mirror, is 5 meters. A digital camera with a 3.2 gigapixel matrix, composed of 189 light-sensitive CCD matrices operating in the ultraviolet, visible, and infrared ranges, will take 15-second exposures every 20 seconds. Given maintenance, poor weather, etc., the camera is expected to take about 200,000 photographs, 1.28 petabytes in uncompressed form, per year, which is far more than can be examined by humans. This telescope in Chile will conduct large-scale sky surveys known as the Legacy Survey of Space and Time, LSST. The LSST survey will cover significant portions of the sky with high sensitivity and frequency of observations, enabling the detection of slowly moving objects on distant orbits, such as the 9th planet. One of the strengths of the LSST is its ability to detect faint objects that might be missed by other telescopes. The Nancy Grace Roman Space Telescope, officially assigned to NASA's mission on February 17, 2016, and scheduled for launch in 2027, is also expected to contribute to the search. The telescope will be used to address tasks such as counting the number of exoplanets in a given galaxy and observing the distribution of galaxies to study dark matter. One of the advantages of Roman will be its large field of view and its ability to take images very quickly. According to digital trends, it will be 1,000 times faster than the Hubble. The Goddard Center estimates that Roman will take about 100,000 images per year. Additionally, ground-based telescopes, such as the ALMA, Atacama Large Millimeter Submillimeter Array, in Chile with its 66 high-precision antennas, and other radio telescopes, can assist in the search through observations of faint radio emissions from TNOs and other objects in this remote region of the solar system. These telescopes can detect weak but significant signals that may indicate the presence of the 9th planet. In 2022, researchers using the ALMA telescope reported that they had detected 2 distant cosmic objects, and other astronomers have suggested that this might be evidence of Planet X, the 9th planet of the solar system, in a serious astronomical journal. It is also possible that missions aimed at exploring the outer regions of the solar system, such as Voyager 1 and 2, launched in 1977, New Horizons, launched on January 19, 2006, and future missions to Jupiter and Saturn could accidentally detect signs of the 9th planet. Such missions often uncover unexpected phenomena, making them potential contributors to solving this mystery. If Planet 9 is discovered in the future, how long would a journey to it take? Some experts believe that we are only a few years away from either discovering or definitively ruling out the existence of this hypothetical world. If Planet 9 is ever found, space agencies like NASA would want to send a probe to visit this distant world. However, they would first need to plan and gain approval for such a mission. It will take at least a decade or more, Andreas Hein, a space systems engineer at the University of Luxembourg, told Live Science in an email. This is mainly due to the fact that missions must undergo a lengthy and rigorous government selection process, he added. However, this process could be expedited depending on how unusual the world appears in initial observations, said Manasvi Lingam, a theoretical astrobiologist at the Florida Institute of Technology, in an email to Live Science. If Planet 9 is anomalous in some respect, there might be greater interest in accelerating such a mission. According to Hein, a private space company like SpaceX could potentially launch missions sooner, possibly within 5 years of the discovery, since they are less hindered by such bureaucracy. Once a probe is sent to Planet 9, The next question is, how long will it take to get there? In 2022, Hein, Lingam, and astronomer Adam Hibbard attempted to answer this question in a theoretical paper published on the preprint server RSIV. In this non-peer-reviewed paper, the researchers estimated that a spacecraft similar to NASA's Voyager probes would likely take between 45 and 75 years to reach Planet 9. These estimates were based on the assumption that Planet 9 is, on average, about 400 astronomical units from the Sun, or 400 times farther from the Sun than Earth. While 75 years may seem like a long time for a one-way trip, it is relatively quick compared to the journeys of existing probes. Mike Brown initially estimated that a probe could potentially reach Planet 9 in just 20 years. However, Lingam noted that it is difficult to understand how it could reach the planet so quickly with current technology. According to Hein and Lingam, reaching Planet 9 could be faster if we were able to master more advanced propulsion technologies, such as light sails, giant sails that capture sunlight, or lasers to accelerate spacecraft. In their 2022 study, scientists estimated that a light sail might take just 7 years to reach Planet 9. However, the team estimates that light sails may not become a reality for at least 20 years. As a result, if we were to find Planet 9 tomorrow, it would be better to send a contemporary probe rather than wait for alternative technologies to develop, said Lingam. Laser sails could be launched later, if and when they become practical and cost-effective. As propulsion systems continue to advance, sending humans to Planet 9 may also become possible, but likely not in the near future. This discovery could be a significant step in understanding the dynamics of planetary system formation, which has direct implications for the search for extraterrestrial life. The influence of massive objects, such as the hypothesized ninth planet, could lead to substantial changes in the architecture of a planetary system. They could act as sources of gravitational perturbations, which in turn might affect the orbits of exoplanets, especially those located within their star's habitable zone. These perturbations could facilitate the migration of planets to orbits where liquid water, a key component for the emergence of life as we know it, could exist. Additionally, gravitational interactions with large objects could influence the stability of climatic conditions on exoplanets, which is also a crucial factor for sustaining life. In turn, understanding these processes could enhance our ability to assess conditions on distant exoplanets, thereby increasing the chances of discovering habitable worlds. Further study of the hypothesized planet could provide new insights into the mechanisms that determine conditions conducive to the emergence of life. This knowledge could become a key element in the search for other worlds capable of supporting life and may potentially lead to significant discoveries in astrobiology and cosmology. The study of the possible orbit of a new planet in the solar system inevitably leads to comparisons with exoplanets in other stellar systems. The orbital characteristics of the hypothetical ninth planet allow parallels to be drawn with planets discovered in other parts of the galaxy. One interesting object for such comparison is the exoplanet discovered in the TRAPPIST-1 system. Located in the constellation Aquarius, 39.5 light-years from the Sun, this system is known for having several planets within its star's habitable zone. Of particular interest is the exoplanet TRAPPIST-1d, which orbits the star TRAPPIST-1 in Aquarius. Its orbit and characteristics might provide useful data for understanding the dynamics of planets in similar conditions. Comparing the orbital parameters of the new planet in the solar system with such exoplanets could help assess its potential stability and interactions with other celestial bodies. Comparing the ninth planet with exoplanets discovered in other systems offers a deeper understanding of how universal the processes of planet formation and evolution might be. This opens new horizons in planetary system research and allows the use of data from other systems to refine hypotheses related to the ninth planet. One key question arising from the comparison of the ninth planet's orbit with those of exoplanets is the influence of neighboring stars on the formation and evolution of orbits. In the case of the solar system, such influence could explain the elongated orbit of the ninth planet, if it indeed exists. This also raises questions about the importance of considering external factors when modeling planetary systems, especially at large distances from the central star. An important aspect of comparing the ninth planet with exoplanets is understanding the processes of planetary migration within planetary systems. If the ninth planet did indeed migrate to its current orbit during the formation of the solar system, it could provide new data on how large planets can move within their systems, altering their structure and dynamics. Studies of exoplanets with similar orbits could confirm or refute such migration scenarios, significantly expanding our understanding of these processes. Could this information also lead to new discoveries within our own solar system?